Hello, everybody. So over the last few years, we have seen now a couple of hundred of binary black hole mergers, but it's still a major question where the binary black holes are coming from. When I did my work here now a few years ago, I remember that after the first detection that we saw, it was pretty clear that everybody was very optimistic about it. Oh, maybe we have, like, once we have 5 or 10 or 20 binary black hole mergers, we would have a rough idea. And it is clearly not the case. And the measures that you're having and looking at, or the measures that people are like originally was thinking about, is the mass and spin. And here over the first part of my talk here, I will go a little bit over some of the observations that people have been doing, some of the highlights from the LIGO. And then I will go a little bit into what I have been thinking about recently, what we can learn from the outliers. So looking just at distributions has been very, very challenging because many of the channels seems to be having very many overlapping features. So maybe there's a lot of learn from the outliers. And so my talk will be on those kind of aspects, and I will mix in later in my talk a lot of physics, so a little bit going all over the place, and try to show you where I think some of the promising directions are in this field here, beyond just trying to get more and more measure and more better estimates for the mass and spin distribution. I think there's a lot of interesting physics that not really have been extracted from these signals yet. So let's get started here, and I'm very happy to also take questions during the talk. Because we might go in all different directions. So if there is a particular topic that I'm then skipping over or going to another one, then I'm very happy to get questions here. First of all, it has been done with a lot of great people at the Niels Bohr Institute. I have a good group here. So I will be especially showing work that I'm doing with my postdoc here, Lauren Zwick, and Gaia Fabi here, who is now defending her PhD. Now, so from these measurements that we have from the gravitational waves that you see here, we all have learned that what we can extract from this is essentially the masses. We can also have an idea of the spin of the black holes. For the spins we might need some more cycles. There will be some modulations in the gravitational wave signal as the spins couple to the orbit and so forth. But it is really difficult to tell exactly how the binary black holes or the individual black holes have formed. It's very difficult to say why did the black holes have the mass that they have. Well, as I will tell you later, there are of course some indications of that there might be black holes that we see out there that have been forming through previous mergers. And one of the indications there is only indirect, right? Is that the spin is peaking around 0.7. And if it's merging with something else, maybe there is a smoking gun. If that black hole that you see have 0.7 in spin is about twice as heavy as the other black holes is merging with, right? But these are all like only indirect measurements of this. So what we really have are all these binary black hole mergers. We see the waveforms, and then we try to probe the underlying distribution or the underlying formation channels. And as I said, you can measure the spin masses, and you can also measure the orbital eccentricity. Right, so the orbital eccentricity comes into the waveform, as you can imagine that the two black holes come very close to each other at pericenter. You send out these bursts of gravitational waves, so you have more like a lighthouse or bursty waveform. I will show you a waveform of that later. So you can definitely also pull that out. The reason why people didn't think too much about that is that gravitational waves, as we all know, tend to circularize the systems at relatively short timescales. So you won't really think this to play a role. But of course, if you're very highly dynamical systems, as I'll show you, there is a chance you have these chance encounters where the black holes are coming in, pairing up on very short timescales, which also then will leave an imprint in the eccentricity. When I'm talking about the formation of binary black holes in different environments, of course, we want to put out some environments that we want to probe and test. So people have been thinking about they could form in the galactic center. In the galactic center, you have many different processes. People here at the Institute have contributed to this field here over several decades. But there, you can split it into different ways. Like, let us say that you have a supermassive black hole in the center here, and you have a lot of stellar mass black holes together with the star. They will mass segregate towards this supermassive black hole that you have in the center, and you might have these single in the counters of your black holes. So they come in and through gravitational wave radiation, they get captured, and then you get these relatively prompt mergers. If the velocity dispersion is very high, this capture can only happen at very close periods in the passages because you have to radiate the excess energy away. So they tend to be relatively highly eccentric. You can also have it, forming in different other ways. If you have a binary black hole, it can, be excited through quasi mechanisms by the supermassive black hole. So there are many, many different ways that you can imagine they could form. Stellar clusters I will come a little bit more into, but these are observational, of course, probe systems here. And we see globular clusters. If just a fraction of the stars are turning into black holes, they will sink to the center through the Spitzer instability, or these processes where you have mass segregation, where the heavy objects kicking out the lighter objects, they sink to the center. You form this small subcluster, and then they start to interact and scatter off each other. And that can also create these binary black hole mergers. You can have stellar multiples. You can have binary stars. Very, very complicated models. I went to a KATP conference last week, and Matthias was there as well, and others that I see here. And just see how rich this field is of binary stars, and a field that keeps evolving with every single observation that they cannot describe. But I guess that you learn something from every new observation. But it is very complex. But I think that the general features of this is that it's very difficult to make eccentric mergers because you have tidal damping, and you have on top of that the gravitational wave damping. Unless that you have these hierarchical triple systems where you form or have these quasi triples, right? So you have the binary star here forms into a binary black hole. You can excite this eccentricity through the outer object here. Or we can imagine many other systems. And there is one particular channel that has been extremely explored here over the last few years. Both because it's fun, it's combining many different physical processes at the same time. Plus, it could actually be a channel that could contribute. And those are these AGN disk channels, where you basically have in the AGN disk, you capture the black holes, or they're forming in situ the disk, they migrate, and because that the migration time at which they migrate depends on the mass. If you have a mass spectrum, the orbits start to overlap as they start to migrate inwards towards the supermassive black hole. That can create some pairing, and that can also give rise to some unique signatures. And I'll come more into how we can probe these, right? So the thing that we are starting to think about is like, what are the smoking guns? Like, what are the outliers? What are the signatures in the gravitational wave signals that they will tell us the difference between the different channels? I can, of course, tell you, if I have an AGN channel and the black holes start accumulating and merging with each other, or maybe the mass function is different, but you can get almost whatever you want. You can have black holes that are merging 100 times with all the other black holes inside the disk. But then those models will only be indirect measures of what is happening. And the same you can do for any of the other models. So the question is, can we go into the gravitational waveform and tell exactly what is happening in the environment? And a lot of the recent work I've been thinking or doing is essentially trying to use the binary black holes as a kind of a clock, right? So if you have been thinking about, well, you all know here that a lot of work on the binary pulsars. Of course, you can try to understand the neutron star and all the properties of the neutron star by looking at the pulses. But if you look at the pulse modulations, given that they're coming with equal intervals, or you understand the mechanism, then you'll be able to probe more or less what the space-time is doing, or what the environment is doing around the pulsar by using these precise clocks. I'm thinking, we a lot of people thinking now that we might be able to use the binary black holes in the same way, right? So we have the gravitational wave, we know how GR is working. If we see something deviating from that, then we can start to probe what is happening around it. And if you think about the AGN disk, we have a lot of gas around. And Michael, you have a question?
I wonder if I'm thinking about, when you say around, are we talking about on the scale of the AGN disk?
Oh, we are talking about very, very local, very, very locally. So one of the leading order effects that I will show here is just center of mass acceleration. So if you just have some mass accumulated nearby, that will accumulate up in your gravitational wave signal. So it could both be stellar companions that tends to be close by. It could be gas that is hardening the system, or resulting in a resultant center of mass in this, or a force in the center of mass of your binary, and all these drifts will show up in your gravitational wave signal. right? So I think it was the rough picture that we had a few years ago where we think, okay, we're going to go in and compare what we get from the dynamical channel and the field binaries. We're going to look at the distribution in spin and masses and possible eccentricity. But as I said, although that this is a very simple test, this is not exactly, that has not exactly returned any answers yet. This here is one of the recent compilations where you see the mass spectrum. It's extremely rich, extremely interesting, and I really have no insight into exactly what is happening, and nobody really, but as you're seeing, people are talking about these different peaks. The peak is around 30, peak is about 10. I think generally you can say that it's very difficult to form binary black hole mergers, or especially neutron star mergers, like low mass binary black hole mergers and neutron star mergers in very dense stellar systems in their clusters. The timescales for them to pair up in the center, all the timescales for them to harden to the point where you can merge within a Hubble time is just too long. So when we're talking about the lower limit here is probably binary evolution. When you start to go up here, there are many other processes happening. Right? And especially people are thinking about this higher mass tail here, where you could form it through these hierarchical mergers where you take two black holes, you get one that's almost twice as large. But then it is all about counted statistics, right? Because if you want to have, say you start out with a cluster with 1,000 black holes and you merge two of them, right? And then you calculate what's the probability that one is then going to merge with one of the 999 black holes. Is much more likely that they will start to interact with each other than interacting with this one that might be a little bit heavier. Right. So for every one that we see as an outlier here, there will come like a swarm of hundreds of other things at the site that we also need to explain. So what I'm thinking, instead of looking at the distribution, this is what we can learn from the outliers. Right? So I will take you through some different ideas and scalings, and possibly some motivation to look into different environments. So can we be guided a little bit by the observations? It's always fun to speculate, and that's what we do most of our time. But now the observations are actually coming in. So can we get guided a little bit towards what kind of outliers that we should be looking for, try to model in our models here? So if you look here, it's a very nice compilation by Isabel Romero-Shore here a couple of years ago, where she looked at measure for the eccentricity. And this is what you see up here. So a small excess here is basically giving you the measure or the indication for a non-zero eccentricity. So eccentricity is down here, and then, or zero eccentricity is down here, and then it grows up here. Right? And then you have the different events down here. And there's a few that stands out. 1905, 21, I'll just show them in a separate slide in a moment. You have one here, you have a few up here, and you have a few up here. It's not entirely clear that what we're seeing is eccentricity or something else, because it is still our template banks are not completely, are not complete yet. So it is very difficult to even probe this here. What she did for this study here was really the best what you could do at that point. We're using eccentric templates, but you had line spins. But what we already know is that when you start to put in spins, you will start to have correlations with what you think could be eccentricity. Yeah.
Sample, because your templates do not include eccentric, that is, are you missing?
I don't think so. No, I don't think so. Then it has to be really extreme. I think what you're missing mostly right now are probably the heavy mass black holes. So for example, here I'm showing, right, so this 1905-21, it's a very weird solve for many different reasons, because it did show some eccentricity, but you can also see what are you fitting the eccentricity to. It's more like just one little wiggle that doesn't correspond, right? So this is the waveform as a function of time for that particular system. And what? There are two models. There is the eccentric, and then there is a circular. Oh, these are no, yeah. So there is no data fitted or put on top here. This is like the best fit, and then you plot how the waveform basically look like. Yeah, right. So you can pick up more or less what the differences are that we are picking out or looking for, In this one here, 92521, which is at a couple of years ago, was the heaviest binary black hole mergers that we have seen so far. Like both of the black holes seems to be above this theorized mass gap. So they had like a 80, 60, 80 solar masses each. But you can also see that you don't really have a lot of wiggles to play around with, which also gives you some freedom in what you want to probe, right? So it could easily be that you don't really have any eccentricity in this one. But on that note, Michael, the point was that when you have higher mass black holes, they start to merge outside of the frequency band. So those are the ones that you might miss, and sources that more looks like plunge-like. Oh, it is just outside of the frequency band. So if you imagine like the LIGO cut off here, if this is like in frequency, oh, this is in time now, but if you have the frequency here and you have the LIGO bucket here where you can pick up, and the lower part here is 10 Hertz, then these here are merging right at the edge here, right? So if you're going backwards in time, you just don't see anything. So this here is an example of the few different signals that you see here. So if we zoom in on one of these here, you can see how the deviations start to build up between the eccentric and the circular, right? And this one here, as I mentioned, was particularly interesting because of these very, very high masses here. And of course, at that point, people start to speculate, how can you form this? And it is right up here in like above the pain stability mass gap, where you think it should be more or less empty if it was just forming from single stellar evolution. So people start to theorize or think about where could you form these black holes that keep merging, and one of them could be the stellar environments. I will show you a few figures of that later. Another one, as I said, could be in these AGN disks where you merge, but the escape velocity is so high about the supermassive black hole that even the gravitational wave kick will not kick you all the way out. So it will stay in the disk, keep migrating, keep merging. Right. So if you look at the distribution here, like you can ask, are these outliers in terms of mass? Right. So now here we look at the chirp mass, which is like the best measure for these systems here, and you can see that so the x-axis here is the chirp mass, and they are not particularly clustered some particular place here. They are following the distribution of the rest of the sample here. And I just wanted to introduce here that sometimes people talk about the eccentricity at peak frequency. So that is when the frequency that have the most power enters 10 Hertz, and that don't have to be the same as the orbital frequency of your binary. Right? So if you have a highly eccentric binary, the peak frequency is determined by basically the pericenter distance, where the orbital frequency is determined by the semi-major axis. So if you have eccentric systems, the peak frequency can be much, much higher than the orbital frequency. So you can see these systems earlier. So that is also why that you tend to have, pick up more eccentricity at the peak frequency, because you see them earlier, where when the orbital frequency enter the band, they have already circularized. So that is why they're lower here. There's a lot of discussion between us that are just calculating stuff and the LIGO people of what should the measure be. But I think on the theoretical side, even talking about eccentricity when things are very eccentric is actually a problem, because eccentricity is that Newtonian prescription of the orbits, but the orbits are precessing and they are shrinking, so it is not a very good measure anyway. So maybe we should come up with a bit at some point. But right, so we were looking at, so just to highlight this one here. You see, you have a lot of cycles in this one here. So we wrote up a paper a couple of months ago where we started to think a little bit about what could the progenitor be to this system here. And Isabel, as I said, she was doing some measures for the eccentricity here. You have the eccentricity at 10 Hertz, but her models did not allow for really high eccentricity. So that is why you see the prior cuts off right here. So she was not able to model things at high eccentricity with the waveforms. But Gupta, postdoc now at the Albert Einstein Institute in Germany, now he had better models that was tuned to numerical relativity, and really was just able to include much higher eccentricity. So his prior was much higher, and you see he actually get, if you believe the data pipeline here, he did actually get a peak in his posterior here. So the eccentricity of this source here seems to be like about 0.4 at 10 Hertz. So we were thinking about what kind of systems could form this here, right? So you can, of course, do a lot of, study a lot of different systems. But a generic test that I thought about was like, can we, yeah, sorry.
Table looks like at 90% the eccentricity.
Let me see. Oh, here, plus and minus isobels. Probably, yeah. So you start to lose the eccentricity when you get down, or the sensitivity here, yeah. So it's really okay. So the error bar here, it's funny enough, it's matching up with this one here. I don't know if it's something that's probably coming from the prior, where it can of course not be less than 0, but of course you would hope that the error bar is smaller than the offset. Yeah. Okay. I was not involved in the data here, but there's still a lot of work on going back and looking at these eccentric systems, because people keep getting these eccentric models better and better. But that's a good point. Very generic test here I was thinking about, because you can imagine a very simplified world here. Let us imagine that the binary black holes are pairing up in the agent. That's more like in a disk plane in the environment, versus binary black holes that could pair up in globular clusters or more dynamical environments in this case here. This here will be driven by isotropic scatterings. You have some binary, something is coming in, it could be pairing up. Whereas in the disk here, maybe you're more restricted to the planar geometry. And the distribution of the probability for seeing highly eccentric signal changes depending on the geometry. So a very simple test could be, is this consistent? Like, is it weird that we see one that's 0.4 and not hundreds that is 0.1 before we're seeing at one at 0.4? Right? So can we get some idea? If I go in and calculate, this is just to illustrate, just take Peter's formulas. I can calculate what is the distribution in pericenter distance, like what is the probability that I have a close encounter within distance r prime. It scales with, within distance r, it scales with the square root r when I'm in a coplanar geometry, whereas if I'm in an isotropic 3-dimensional, it will be proportional to r. This is coming from standard Newtonian distribution functions, so it has nothing to do with GR, but we can test these two models here and ask, do we expect more or less eccentric mergers above or below 0.4? Right. So, and in fact, it was not so easy to tell any, or put any strong constraints on this, because if you say, so here this is a probability of getting an eccentricity greater than some value at 10 Hertz, where I normalize it to 0.4. Okay, so it means that, and you have now to, so I had to do it for different harmonics because they're looking at that in the data. But if you look at the 3-dimensional case, it's a solid curve here, and then the red one here, it will basically tell me that I will see for every binary black hole merger with an eccentricity of 0.4, if the scattering is coming from, or the pairing is coming from an isotropic, I would expect to have seen 3 that is above 0.1. Okay, so it's not like 1 to 100, so it's not like an outlier in that sense. And it's the same with the 2D. When I push it into a plane, maybe I've seen like 1 or 2 above 0.1 compared to the one I saw at 0.4. So it is not, so these, just a single observation at 0.4 doesn't really tell us much about. If it was 0.999, we could have gotten an idea, but 0.4 is not really. We tried to understand if it could form in a cluster, and it did. So we asked Carl Rodriguez, who has been doing a lot of work on this, and he shared his data with us. And he took like a globular cluster simulation. It's a compilation of the whole catalog that they have, and calculate the eccentricity at 10 Hertz. And this here is the distribution as a function of, say, the total mass. And the two different estimates from Isobel and Gupta are shown here with different, right? So it could possibly have formed in a globular cluster. Another weird measurement, clearly outlier, was a claimed detection of a center of mass acceleration of a binary. And I'll go much more into this in a moment here. Let us just play along and think and believe that this is actually a true observation. Then what do they claim to have seen here? They have claimed to have seen in 9 to the 14 is a system where you have one of the components being relatively light compared to the other one, they have claimed to see an center of mass acceleration. Okay, so what does it mean? So when you have objects that are orbiting around something else, okay, and in this case here, an eccentric orbit, doesn't really matter. I have my heavier black hole here, and then I have my source, my gravitational wave source is orbiting it. Then as I'm sitting down here as an observer and looking at my source here, I have a binary that is moving on this curved path, and I have a binary here that's moving on my straight unperturbed path. Can I tell the difference? Which is basically a mapping of the eccentricity. And I can, because as I'm sitting here as an observer, I will see a time-changing time lag between the unperturbed and the path here that is being bent, right? And this time lag here to Newtonian order is just a half a t squared plus, you know, the higher order terms, a dot and so forth. So this is just a Taylor expansion around the straight line here. And you can see here that this one here, first, I can go in and quantify it, say it's a time-dependent measure of my mass here, because what we know, you know, from the Doppler theory, like we have 1 plus c, the cosmological stretching of my waves. I have 1 plus c Doppler. It could be the whole system is moving, but then I have this extra term, which is a, the acceleration, times t divided by c. So it's a time-changing Doppler shift, and that is why I can pick it out. And they have claimed to have seen this, right? Okay, so we have been writing several papers in this even before this this detection came out, and you can of course extend this to any acceleration for any orbit here. I'll show you a few situations later. But it is propagating to what we call this phase shift of your gravitational wave signal. And the phase shift you can think about as being this displacement in time, being the time lag as a function of time as you're going backwards from the merger. And this phase shift is like an orbital offset like in orbital angles, right? And if you calculate what is that phase shift as a function of frequency as you're going backwards, it's going f to the minus 13 third. So it's very, very steep power law. So if you're just going to go a little bit backwards in time, you can accumulate an enormous amount of phase shift. For LIGO, you're barely, you know, you only have a few cycles. So it was, you can say, is it by luck that they found this one here? You know, of course it could have been by luck. There are many, many things that were raised about this study here. So I think we can, I will later show you that might give it a red flag, but it is an interesting new direction that many people are starting to work on. Yeah.
So you get a detectable phase shift, you want some other object nearby?
Yes.
Stability arguments that one can make?
Exactly. Yes, exactly. Yeah. Yes, and the tidal force, how could it have formed? You know, what's the frequency compared to how close it is? Yeah, you're absolutely right. Yeah, we have calculated a lot of limits, and that I can try to show it to you later. Yeah, but you're absolutely right.
You were just raising concerns about the data themselves and whether
it is not the data itself; it's about how they use the data. Yeah. My PhD student has tried to reconstruct this one here, and many others have tried it, and they have not been able to do it. They have found some common mistakes that one could have done that seems to reproduce it.
Reproduce it from the data?
Yeah, from the data. Yeah. Right. So if you're going in and say, okay, so how can we go in and probe the environment with these accelerations? Well, it is difficult, right? Because you are going in, and I said you have to leading order, you measure an acceleration. Most of the time, you don't measure these higher order terms just because that they will be suppressed by, you know, even higher factors of the in-spiral time relative to the outer orbital time. That's often very small. So it's always a combination of m over r squared that we are measuring. So is it because that this source here was very close to the supermassive black hole, or, you know, relatively far compared to the distance to the supermassive black hole, or was it because it was relatively close to a stellar mass black hole? So I will show you some different ideas on that about that later. Oh, actually, by the way, at Baccalaureate, I will give some ideas on how you can break this m over r square. So I will not have time to go into the things here. But as I said, it's interesting. A lot of people are making these pipelines, but this first claim, I think many people are giving it a red flag here. Very briefly, there has been, as I said, some observations recently on these two events here that seems to have chi-effective that are, one is, so if you have a minus, like a negative chi-effective, meaning that the spin is opposite to the orbital angular momentum, and then you have one here that is aligned. But the point is that the effective spin here are very close to 0.7. Okay, so that is the spin that you would get if you just take two black holes and merge them. At the same time here, you can look here at the mass ratio, and that is pretty close to 0.5 for both of these events. So does it indicate that you have a cluster with two black holes merge and then they're pairing up again? There was no sign of eccentricity, so we cannot really do any studies on the dynamics in that sense here. But as I said here, the general feature would be something like this. You take and merge two, and then you get a new black hole that is pairing up. Can we imagine some systems that could do that? So we could go back to the globular clusters. And then if we take these globular clusters here, where you have multiple interactions and ask what would the distribution and number of these second generation mergers be? It depends strongly on this initial spin of your black holes. So if you have initially spinning black holes, even at a critical spin of 0.1, 0.2, 0.3, and two of them are merging, they'll get an enormous kick and just be kicked out of the cluster. So it's extremely difficult to build up this higher generation of black hole mergers. Where in the HN disk channel, where everything is possible, especially this case here, you will be able to kick it out a little bit into the disk. It will not be able to escape exactly. It will probably go back again, and then you can keep on going. So how do we constrain the origin with all these different things I've been talking about here? So now let's dive a little bit into the physics and go a little bit different directions and see where it will take us. Right? So let us think about what signatures would you expect from these very dense stellar systems. Maybe some of you saw this movie here, but what is driving the interaction or many of the processes in these very dense stellar systems is the interaction of binaries with other objects. And here you see this classical binary single interaction here, which on a classical level, provides heat source to the cluster. It doesn't collapse. You have the black holes pairing up in the center or the binary stars. But if I consider the black holes instead of just the stars, then the excitation of the eccentricity that the third object here provides on the binary here sometimes bring it into a case where the in-spiral time that I will get by just exciting the eccentricity is comparable with the orbital time of my system. So then I will have these mergers that are happening on basically the orbital time of my system here. And you can see, even though it looks very, it's a very rare case, you can see I have a lot of chances for undergoing these closed passages. So a relative high fraction of all the binary black hole mergers inside the clusters do form in this way, about 10%. So we can try to understand what is the distribution of all these frequent interactions, and can they tell us something about what we have observed so far? So we can split it up in these interaction channels, let us say, or outcomes. So if we have a binary here undergoing interaction with a single object here, the classical way that it's going to happen is that it's just going to interact with this object here, not the same binary, but it keep exchanging until that the center of mass kick of my binary, my single, is enough to split it up so the binary and the single leaves the cluster. Outside of the cluster, it will might merge within a Hubble time. You have another case where the frequent excitation of the eccentricity is such that the binary black hole that is floating around inside the cluster here will merge before it undergoes this next interaction. And as I showed you, there's a third option where the binary black holes are merging while they're still bound to the third object that is creating this triple, right? So you can split it into these different channels here. This here, the characteristic time scale is the Hubble time. You produce a binary, has to merge within a Hubble time. This case here, it has to merge within characteristic interaction time scale, 1 over n sigma v. Where this one here has to merge within a characteristic orbital time scale. So it's all split up by the orbital time scales. If I now plot the different distributions, so just to make sure here, the ejected mergers, so in the next one, I'll only show the two-body mergers and the three-body mergers. And the two-body mergers are the green one. So those are the ones that are forming inside the cluster in between your scatterings. And I'm plotting here the strain as a function of the frequency, of the peak frequency. evolution is coming up here, and we expect them to see some of them eccentric in the LISA band. 3-body mergers eccentric in the LIGO band. So if we start to see these things as a function, in the full frequency space, we can start to take the spectrum of these clusters in terms of frequency and eccentricity space. So there has been a lot of work on this, and this is the general picture. So for example, here you have results from full globular cluster simulations. The other one was just from my small calculations, and you see the same picture. You have, depending on the different interaction channels happening inside your cluster, they will split into different measures, and this is what you're going to pick up here in the frequency space and in this brain. And as I said here, it's all depending on the different characteristic timescales. So if I make my cluster less heavy or more heavy, the timescales are going to change, and then the distribution starts to shift around. So you can measure exactly the properties of the clusters and the richness of the dense stellar systems by looking at these spectra here. Well, but let us take a look a little bit on are there any questions to the cluster part here? So let us go a little bit further and think about how might the binary black holes form these famous AGN disks that I was just talking about. Right, so the picture is, as I said, you form or have the black holes inside the disk. They start to migrate through the disk. They might pick up each other, and then they will merge in different ways. Once they pick up each other, they form a binary. They might start migrating, or they keep migrating through the disk. Now they have a double mass. They migrate. The migration might be slightly different because you have a binary. Maybe it's forming a gap and this and that. Don't think about that. We just think about that they might keep migrating, and then they might interact with other objects. So this is an example of just a classical treble scattering when they interact with another object inside the disk. I have an interaction with the gas that you're going to see in a moment. But the problem or the point here is that, as I said, that if you're pushing, so this here is the probability to form a highly centric merger as a function of the orbital inclination. I have my binary here, and then I send in objects here. And the only thing I'm doing is I'm probing here the disk limit, and here's the isotropic cluster limit. The only thing I'm doing is that if I'm going from the isotropic case and push it down to the disk limit, the number of eccentric mergers can be boosted by 2 orders of magnitude. So why are we thinking about clusters if we can produce the eccentric mergers with this one? Of course, you have variations in the inclinations. So that and you can see it goes very, very steeply. What? Okay, so the 2 lines up here are calculated from the theory that I said, square root R and R, where these here are from numerical simulations. People have found this in planetary physics as well. What? No, this is without the gas. If you put in the gas, I'll show you a simulation of that later. It just becomes even more strong. It is very difficult to control the. That's of course a very risk, because do you circularize before you get to the band, right? So there's a lot of stuff in there. Now I argued that there are many different ways that you can create these eccentric mergers. So are we not left with where we started with? Okay, now I explained about eccentricity. What can you use it for? If there are many different paths going towards it. But now we're going to come back to this question of trying to understand the signals a little better. Because now let us take a look at what we actually see at this figure here. This here was the example of my binary black hole forming in the cluster. And what you see here, you notice this curvature here. And if you have 2 black holes that are just pairing up by a single capture, there is no curvature, just going to pair up, and it's going to fly away, and it's going to merge. Let's think about what you can learn from this curvature here. And I kind of already gave you the answer earlier, because what is happening is that as the binary black hole merges close to something else, and you're sitting here as an observer, I can write a small code that just tells me how much is the signal stretched from this time-changing time lag here. It's a very, very simple calculation. And as I said, it's completely the same as what people have been doing with the binary pulsar. So you can put in all those machinery of how the waves are modulated, relativistic effects, beaming, all kind of stuff. Right? Now I'm just going to show you results from the Newtonian limit, where you just have this time lag between the unperturbed and the perturbed path. And we wrote this code here. This is simply just to tell you that we just put in the post-Newtonian terms. You have precision terms, you have radiation terms. We did not include higher order terms. And the idea here was to try to study the observables that we might get from these systems. So you're starting out, in this example, I'm starting out with a binary here orbiting a black hole. It's orbiting the black hole here, and then I evolve the system forward until merger. Now at merger, I remove this black hole here. And then I just take my post-Newtonian equations and evolve them backwards. So I keep my black holes here, and then I just go backwards. And then I put my observer somewhere, and then I ask, what does that observer see? Does the observer see something different? Is it just this time lag that I talked about, or are there other effects? And there are, of course, tons of other effects that are buried in the signal that you're not able to describe with this very simple prescription I showed you. One of the effects is a modulation in the frequency. So if I plot here the frequency of my gravitational wave signal as a function of time leading up to merger, this here is the peak frequency. So the peak frequency, if it's unperturbed, should just go steadily and go up and rise until merger. But what I see are these modulations in my signal. Where do they come from? Well, it's just coming from a coupling between my binary as it's precessing around itself, and then being coupled to the black hole here. So you can imagine that when the binary black hole points towards the black hole, it experiences some tidal force compared to if the orbit is perpendicular to. Right? So this here that you essentially see here is a measure of the precession timescale. And you also have tidal effects that are pushing and pulling. This is exactly what you're seeing here. So if I'm looking, for example, as what I call this phase shift, the deviation from the unperturbed and the perturbed, as a function of time leading up to merger, I have the time lag effect that I talked about, the Römer time delay. This is the red line. And then I also have this bluish here is the contribution from the tidal effects. So as you're going backwards in time here, tides, of course, play a larger and larger role. At some point, it just explodes. That relates a little bit to your problem or your question. Our point is that how do we even start out these systems? It has to be heel stable at some point, and there has to be some correlations. And we can talk about that. You can put some limits on it. When we did this work here, there was a lot of papers out on this kind of stuff here where they didn't include the precession. And this is just an illustration of that. If you don't include the correct precession terms in this problem here, you just pump tidal energy into the binary, it just expands and you get enormous phase shifts. Okay, so that was just a rake flat on that. As I said here, when you go in and calculate the phase shift as a function of frequency, you get this characteristic f to the minus 13/3 curve. So this is the dashed line here. And this one here shows a source where it basically forms here, and then it evolves. And then what we do here is also try to take into account the effect from eccentricity. And I wanted to show you a little bit, just give you an idea of how eccentric sources can give you orders of magnitude better estimate on these phase shifts than what people normally have been thinking about in terms of circular sources. The reason is, let us look at a circular source, it's the black curve here. And, in standard physics, you can say, how well can I measure a displacement of this waveform? Probably not better than within some fraction of the orbital evolution, right? So you have some natural blowing here. But you can see when you have highly eccentric sources, your measure is much more sharp, right? So it basically corresponds to have a much sharper pulse signal. So you can go in and calculate these deviations to much, much higher precision. That is one effect. The other effect is that the peak frequency enters the band earlier than the orbital frequency. So you will be able to see the source at relative lower frequencies compared to if it was a circular source. And you saw that phase shift cost, will scale f to the minus 13/3. So if you can catch the system when it's still slightly eccentric as it's driving into band, you can pick up these phase shifts with orders of magnitude in the increasement. We're starting to explore this. We wrote just a couple of illustrative papers on this here. And it's, so leading order can just show that the phase shift that you get in a boost is more or less just the peak harmonic, like the number n is the peak harmonic times the phase shift you just get from the circular evolution. So if you have a highly eccentric source, peak harmonic n equals say 100, you'll get a boost of 100. So this is exactly what I'm showing here. It comes in the eccentric source coming here, and then you will catch it early unpained. So do we see some of these eccentric or these phase shifted sources? So for example, here I'm showing a chaotic scattering, and we can explore a little bit what we can learn from it, because you see all the calculations that I showed you so far was with a half at squared. You assume the acceleration is linear, but in many cases here you also see part of the orbit, and that will also show up in the phase shift. So you can actually measure the whole triple orbital configuration through this way here. This is just a few examples showing that depending on the geometry and so forth and where it's merging, if it's merging the apicenter, of course you will have huge phase shifts. If it's merging more the apocenter in these triples, and then you have less. So there's a lot of information there. A distribution of the phase shift here is a function of peak frequency. We have not really finished the study yet, but if we are doing thousands of these scatterings, we see a high fraction of our triple scatterings that do have high phase shifts. Where do they come from? It's simply just the chaotic nature of the system. Sometimes the binary here merges while the third object is nearby. And we have hundreds of these examples. Scattering here again, classical scattering. This binary here is trying to merge while it's bouncing off this object here, which is still bound to it. Right? And this is another example. This is coming almost head-on relative to this one here. All of these scatterings here will give rise to phase shifts. And these here are not fine-tuned. They're just, a part of the statistical tail of these interactions that we know are taking place in these systems. So I'm gonna finish off with some thoughts on what we can learn about phase shifts in terms of AGN disks, because then you start to have gas. And I just want to introduce this very rich picture of what is happening when you actually start to put in the gas. You can imagine that the binary black holes form here, different places inside the disk. Some of them might form close to the supermassive black hole. Some of them might form further out. If you have the triple scatterings, as I already showed you, the presence of the third object might be able to generate some phase shift, where the one that are forming closer to the supermassive black hole just get the phase shift or the acceleration from the supermassive black hole in itself. We did have a recent paper out on this, but I just want to I can highlight a little bit here. So this here is the phase shift again as a function of frequency, where you see the different tracks. So for example, here you see a source forming here. It's evolving, and then at some point it enters the LIGO band, and this is the value that you see here. These here are the one where there is no triple scattering. So the phase shift here is entirely driven by the supermassive black hole in the center, where the yellow ones up here are the one where there is a third object. The sampling that we are doing this from are 1D simulations of AGN pairing models. I can come more into that if you want to know about that. But I wanted to go to this point here of a paper that we put out a few months ago with led by Conor Rowan, also at the Niels Bohr Institute, where he did the first scatterings of triples in gas. The main takeaway here is that the relative distance between your objects as they're spiraling in decreases by orders of magnitude. Okay, now I'm not talking about all the small effects and how it can create torques on the black holes and so forth. The whole system, if you put these three objects into this system here, of course, because of all the slushing of gas that's pushed out, it shrinks by orders of magnitude. What does it tell you about the acceleration? It goes as 1 over r squared, so it can boost this acceleration by orders of magnitude. It will not be captured by the standard dynamical friction work, so you really have to go in and understand the slushing of the gas here. So a few examples of our scattering. So normally when you have without gas, it's very difficult to shrink the system, because immediately when something sinks, there is energy conservation. You kick the third out and then the interaction is over. But here you have enormous reservoir of gas where you just keep kicking and you put all your orbital energy into the surrounding gas, and the system just shrinks and shrinks and shrinks. So if we are going in and calculating, so the gray lines here are here's a few examples of binaries without this gaseous force here, and we're going out now and calculate what would the enhancement be from the gaseous shrinkage. Then we push many of these binaries well above the sensitivity in the LIGO band. But we didn't do any detailed explanation of this yet. We only had a few simulations to guide us, so there's a lot of rich stuff to understand here. The last slide here is work by my PhD student, Gaia Fabi, and also together with Alexander Dittman. And we were trying to understand the importance of the binary alignment inside the disks. Right? So there's an interesting little thing that we found here. And that is that if you do scatterings, let us assume that you have a scattering happening inside an AGN disk or whatever. When you form a highly centric binary, as a result of this, of course, the angular momentum vector will be relatively small, so it's easy to tilt around the binary. Right? So even though that you started out with something that might be coplanar or associated with the disk, if the remnant binary is highly centric, it's easy to tilt it around. So if you form a highly centric binary, it might be tilted with respect to the disk. Now the question is, will it be able to merge before the disk realigns it? Because if the disk realigns it, then you will end up with these chi-effective very close to 1, right? So the spins of your black holes, right? So you have a very nice illustration here. You have 2 black holes here. The spins are pointing in this direction. After the scattering, the spins, of course, are still pointing in the same direction, but the orbital have gained a tilt, right? The question is, will it be able to realign before it's merging? And as I said, highly centric binaries, they will have very small angular momentum, so they will be highly tilted, but they also merge very quickly. So the question is there a correlation between eccentricity and chi-effective? If there is, it will tell us about the processes, the gaseous processes that are happening in these disks, and we explored this. Of course, it's an exceptionally rich problem also that Alex was helping a little bit with in terms of some of the calculations, but doing this full problem here with the scatterings is just not something we have done yet, but at least it's pointing in some direction of where some interesting observable consequences could happen. So this is what I had for you here, and I wanted to tell you that I still haven't told you exactly how you can tell the difference between the different origins, because what you measure is just acceleration. Is it gas? Is it a supermassive black hole? What is it? At Bakar lunch, I will present you a little crazy idea that I put out this morning on Archive. So I hope I'll see many of you there. Thank you.
Thanks for the talk. I wanted to ask, what happens to those phase shifts if you think about some external encounters with other stars?
Internal encounter, well, so things that are just passing close by, or like normally that. So the point is that you need some kind of fine tuning, right? So if you not need something to merge while something is flying by chance close by, that probability is 0. But you can think about if you go to the LISA band in the state, right? There's of course many people saying, oh, why don't you go to the LISA band? You have hundreds of cycles, 1,000 of cycles. Many of the binary black, like essentially all of the things that we're looking at here would never show up in the LISA band. They're formed on such a strong environments that, coming back to your point, Ilya, that if you actually put a threshold on how could they have formed, what is the initial frequency, how close to it have been, all of them are forming at the higher frequencies, and everybody finds this now. So if you want to think about something that where this could be important, you need something in the LISA band, and maybe hope something would fly by over this 4 years timescale. But I don't think that the probability is comparable with the other things, but we can think about it.
So lots of pretty pictures of things spiraling around each other in orbits, but what we actually measure is a waveform.
So waveform, yeah.
So have you actually calculated what your waveforms look like, what the degeneracies are that you get confused? Because you seem to have sort of taken sources and perturbed them and asked how they've been perturbed.
Okay, so that's a very good point. There are 2 points of this. So if I'm thinking about the tidal forces that are pushing and pulling, that's very complicated. If I want people to do the NR simulations of that, I need to, basically redo all the NR simulations, and you have to understand how, it couples with the post-Newtonian precision terms. I'm trying to put together some ideas how I can include some of the tidal coupling modes with the EOB models, which is the closest one you can get to this. So I do have some ideas on that. But all of the other effects that I'm talking about, center of mass acceleration, all this, are basically just a term that you multiply on all the frequency bands or banks or template banks you already have. Because once you have your waveform, the only thing that really changes is where I'm looking from. And the only factor you really have to multiply is just 1 plus A times T over C. And then you play around with this time-dependent stretching A.
You changed it.
That's a very good point. Okay, so okay, that is a very good point. So if I'm going in and calculate the effective phase shift from not including eccentricity, it will go something like f to the minus, I think, 11 third, close to 13 third. So there are problems, but it will not mix with the chirp mass, only to low order. So on the theory level, they're all different, but practically they might be able to mix here.
Just wanted to understand the rates. So let's take the globular cluster channel. Of all mergers in globular clusters, what is the expectation for how often either eccentric or you'll be able to detect some phase shift from a strong free body?
So in terms of these three-body mergers that I showed where something is bound to, it's about 10% of all the mergers from globular clusters. If you say, and that is not just me multiplying stuff. Well, it was first, but then somebody else actually did the scattering with and you find that number. And then you have to put a threshold saying, okay, can I measure an eccentricity of this and that, and what is the frequency? Then you're maybe half that at the LIGO, about 5% in LIGO you should be able to see. And then a fraction of them will have this phase shift, and we are currently trying to calculate that fraction. Yeah, I think my point is that there's a lot of people looking at these phase shifts, and we started this new center in Copenhagen called the Center of Gravity. 9 out of 10 in this center is looking at perturbations from modified gravity, boson clouds, spiky dark matter, all this stuff that have gained a lot of interest because now you can test it with these phase shift models. Here I'm saying that I'm trying to explore all the different ways that nature actually can create these things here, right? So we are working on the rates. Right now we think about them as outliers, but we need some more work to get the right rates out.
So at the end of the 5, when we have thousands of mergers, you're confident?
People are already, well, as you can, I would see a few of them but then you are back to your original point. Is there a probability to see a phase shifted source without that also being eccentric, right? There has to be some correlations, because how do I put a circular source next to something else? If you go 5 orbits back, it was Hill unstable. How would have created such a system? So there are many corners of the space where you can start to. So that is the right way of thinking about it.
Yeah. So if you were able to go earlier, then you would get quite a bit more information because the phase shifts build up.
Yeah.
If you have a source which you're cutting off because you're out of band, but is there any way to go back in the data knowing that you have a source and with some model for the backgrounds and try to dig a little bit more information out of the signal there?
I think in terms of the eccentricity, as I was saying, if you can pick up a little bit of the modes that are coming in before your peak harmonic, and as I was discussing with people last week, if you have these high mass ratios, and maybe you can learn something from the higher order modes that might be coming in. Matthias, you were a little skeptical because you have exponential cutoff in your signal to noise but everything that comes in a little bit earlier than your peak harmonic will help you.
Okay, let's carry on the conversation.